Hello everyone, welcome to the vocabulary of physics. Today in this video we are going to discuss about concept of matter. Okay, let's get into it. This is one of the fundamental concepts in physics. So first of all, what's the matter? See, whenever we are going to define a fundamental concept, right, it will be very tough. It won't be very straightforward like advanced level concepts. There will be a lot of roundabout way to go about it. So I'm going to take a working definition. Working definition meaning it is a tentative definition. All the scientists may not agree with a single definition when you're dealing with a fundamental quantity like matter. So working definition, I look at it in two ways. One is the macro scale. In macro scale meaning at a daily life situation or beyond that, bigger scale if you consider. Matter is something which occupies the space. It will have a volume. Volume need not be definite. If it's a solid or liquid, it will have a defined volume. But if it's gas, it can occupy any amount of volume. But it will be having a volume definitely. And then you have always a sense of touch. A material and matter can be touched and then felt. Even the gas also can be felt by blowing over your body. So touch is compulsory, but you may not be able to see all the matter particles. Like for example, glass may be transparent, air may be transparent. Some of them may be having smell, they may not have smell, a taste or no taste. So those are all things not necessary, but touch is definite. So the next we have this quantum scale. Quantum scale meaning when you go to the bottommost level, elementary particle level. That is a modern uh, kind of scale right now. At this point in time, this is quantum scale. At this level, they say if you have two matter particles, they cannot occupy a particular location simultaneously. This is called Pauli's exclusion principle. Any matter particle, if you have the like particle and you try to bring them to the same location, that's not possible. That is one important property of a matter. That's how they define. And they also call something called rest mass. We'll be going on discussing about what is rest mass and all. A matter particle must necessarily have a rest mass. These two properties must be present to say that it is a matter particle. That's a definition of it. Then the next thing is most important philosophical question or most intriguing question over the centuries is that what is matter made up of, right? When you cut it, what is there inside? So we want to understand it. So that's where we have the historical perspective. Over the years, there are so many ways that has been defined, like what is matter made up of. Early days where you don't have any labs, experimentation, microscope and all that. That's where you have to use your mind and all to visualize what is matter. So that's where you have this. Earlier we had this 5 elements: earth, water, air, fire, and ether. Ether is some new kind of medium which is pervading throughout the space. That's one idea. So they assume that every matter particle is made up of these 5 elements. That was the original thought over the centuries. And after that, around 600 BC, Indian philosophers, Indian sages like Kannada or Kannad in the Hindi, and there are some Jain rishis also who worked on it. They had this idea, floating the idea. There is a minute particle called atom, which cannot be destroyed or it is indestructible. So you cut the body into small pieces, you go to that level. That was the idea floated by Indian people at 600 BC. But later 400 BC, Greek philosopher independently, Democritus, he also proposed the same kind of idea that atom cannot be destroyed. It has got a definite shape and size that is indistinguishable. So you keep cutting the body into smaller and smaller pieces. Finally, you will be ending up with the atom. That's what the proposal he has made. But after that, Aristotle came and there was a debate or discussion. Aristotle says, no, nothing like that. A matter can be cut into indefinite ways of particle, meaning he was thinking matter is like continuum. There is nothing in discrete particles. You can keep on cutting forever. There is no limit to it. There is no atom property. Because Aristotle was so popular, so this particular idea has come to fore, and then Democritus' idea was put aside. For so many decades, it went on like this until this 17th century, where this rise of logic and then reasoning, we call it as age of enlightenment. That's where many scientists have come. Like for example, Newton. So he was very famous for many other things like optics and gravitation and Newton's laws of motion. But he also was famous, at least secretly, he has been doing a lot of work on alchemy. In the sense, you take different objects, different materials, you want to convert that into gold. That was the idea they had. So he was working on alchemy. So he worked a lot on mercury, and they say that he was poisoned by because of the mercury, and that caused him eventually his death. So he was working a lot about materials, properties of material, understanding the material properties and all. Galileo is the one who actually introduced the concept of experimentation. So anything that has to be experimentally observed for it to be treated as a truth. That's how he has proposed. And after that, Lavoisier, he is the one who actually proposed this periodic table. He is considered to be the father of periodic table. A lot of chemical things have happened. And same way Franklin. These are some scientists we are talking about. It's not the exhaustive list, but they are most important people who worked on it. He was very popular and he was in the power. So he pushed that experimentation, theoretical and all that. So this is one more important thing. And during this period, again, this atom, the idea of atom has come back again. Then comes the next level where some more scientists like J.J. Thomson, he discovered electrons, cathode rays. Rutherford, he worked on nucleus. He identified the concept of nucleus. So he said that there is atom. Inside the atom, there is a lot of empty space, only very tiny piece of region where the entire mass is concentrated. So nucleus has been identified. Bohr, he said, okay, now that there is a structure of atom, atom is not completely whole. There are some gaps. You can cut that into pieces like electron and nucleus. He said there is a nucleus like sun here in the solar system. Around the nucleus, planets are moving, like electrons are moving in that way. He proposed. And Millikan is the one who did experimentation to prove that electron charge is 1.6 in 10 power minus 19 coulomb negative. Mass of electron was also proposed by him. So this is a very important idea where they say that atom is not indestructible. You can break it. You can break it into pieces and go on further ahead. And after that, they thought nucleus was a fixed one, but suddenly they said, okay, nucleus also can be broken into pieces. Chadwick is the one who discovered neutrons, and then Goldstein is the one who discovered these positive rays, protons, and so on. So they said that nucleus also can be broken into pieces into neutrons and protons. At this point in time, they said, what is matter made up of? Molecules and atoms, which are further made up of neutrons, protons, and electrons. That's what they had come to. Later on, they say that even protons can be broken into pieces. Protons are not the elemental particles, they are composite particles. Even neutrons can be broken into pieces. So a proton or a neutron are made up of quarks, and they are gelled together because of field particles called gluons. So that's what they say. That's how they, of course, quarks were never discovered directly, but there are some experiments which indicate the presence of quarks indirectly. This is the thing that we have here. Now the question is, can we break them further? Is there any further breaking of quarks to see what is elementary to these? So this discovery, this particular process of exploration will continue like that. Now, where are we staying? So if I have to tell you overview, when I say what is matter, it depends on at what scale you are observing. At macro scale, it is solid, liquid, gases, and then you have plasma, meaning gas of ions and charges. And then you have at low temperature, boson-Einstein condensate, they say. So that's a different kind of matter. Of course, quarks, plasma is also proposed. So that is one state you have. This is very rare to identify. These things are generally observed. And then you have at microscopic view, when you go into the microscope and then try to observe them, you don't see them as continuum, you see them as molecules and atoms, like DNA is a molecule. Atoms, which are the subparts of molecule. And if you go further down, where you need to do some high level experimentation to identify protons, neutrons, and electrons. And then further down, you have quarks and leptons. Leptons meaning there are so many particles. Example is one electron, positron, neutron, and all those. So you will study that as you go on. But these are the things finally we are right now. So if you look at the scale, macro is this crystal 10 power minus 9 meters. Further down, you go at 10 power minus 10 meters, you will be entering into atom. 10 power minus 14 meters, you will be entering into nucleus. 10 power minus 15 meters, you will be entering at the level of neutrons and protons. And then if you go 10 power minus 18 and below that, that's where you will be going into the size of the quarks. That's what it is. So as of now, we are staying here. We don't know whether we can go further down, depending on the advancement of the experimental feasibility, or is it going to be the final thing? We don't know. So that's where we are right now to understand the matter. Finally, there could be some confusion between matter and mass. Matter is not mass. Matter is an entity, mass is a property. So matter has so many properties like mass. Matter exhibits mass as one property, because of which you will be experiencing gravitational forces, and also inertia of motion. This is one property. Matter also exhibits charge. There are two types of charges. One is electric charge, using which you will have experienced electromagnetic forces and so on. And there is color charge at nuclear level. Because of that, there are some strong nuclear forces. Quantum spin, that's related to angular momentum of the elementary particles and so on. So these are the properties of the matter that you have. So matter has a property which is mass. So please understand that that's a very important difference in physics. But in daily life situation, many times we use mass and matter interchangeably. But here very clearly we have it. One more important thing here, mass is not the fundamental property of matter. So there are some particles which are not matter particle, but they are associated with matter. That's very interesting, like gluons. They are field particles, and also bosons. They are associated with mass. That is very interesting phenomena when you go to particle physics. So matter is one entity which exhibits the property of mass. Mass is not the property of matter alone. There are other things also which exhibit. So it goes very interesting or confusing as you go down further. And then finally, what is ahead now? So matter, okay, we understand. But now there is something called antimatter. For example, electron and positron. Their electron is matter, ordinary matter. Positron is considered to be antimatter. That antimatters you don't see very much here. On the surface of Earth, we will have almost nothing. Because the moment you combine antimatter and matter together, they explode or they annihilate each other to produce energy. So that is there. Antimatter is not hypothetical. It is very much experimentally observed and clearly understood. When you go into 12th class, you will study about positron, antineutrino, and so on. They are antimatter particles. Antiproton is one more. There's one more concept of dark matter. Dark matter is the one which cannot be visible for us. It does not interact with electromagnetic waves, but it is considered to be or proposed to be present there. So it is not yet identified. This is only a proposal. We see that universe is expanding at an increasing rate. So that many telescopes and all, they are able to show that. So by observing the rate at which the universe is expanding, they are not able to give explanation to it with the existing matter in the universe or expected matter, estimated matter in the universe. They say that there must be more than that. That is considered to be dark matter, which cannot be seen but can only be observed with the gravitational effect. They say that nearly it will be about 85% of the total matter in the entire. So ordinary matter is probably about 15%. Dark matter, dark energy together probably around 85%. That's a proposal we have. It has not been confirmed. So once it is confirmed, it will come in your textbook. But this is what happening. Right now, this is the discussion that is happening at the scientist discovery, scientist exploratory level. So that's what we have here for this about the matter. I hope you understood and enjoyed. So for more such kind of videos, we'll join again. Thank you very much for joining. And until next time, goodbye.